Okay, so let's start with a brief summary of what we have been doing so far. We have been interested in the singularities that occur in Feynman integrals, okay, and we are looking at multi-loop Feynman integrals. So there are many loops, and we have seen that if maybe I should write down the expression just to remind you. So if you look at an integral which depends on external momenta pi, okay, you can have any number of lines, any number of loops, and this is given by integral over the Feynman parameters corresponding to each line. I think I used n for that, it's correct, okay, and then you have a delta function times some numerator which will depend on the alphas, the loop momenta k, okay, k1, k2, so forth, and the external momenta pi. Okay, and you remember the origin of alpha and k's and pi in the numerator. Okay, fermions will, by multiplying a p, k slash plus m will bring it there, and it's multiplying a over alpha. So that's how it comes here. And we had combined all the denominators, all the propagators with their alphas into a big D, which is alpha. You can put whatever you like, doesn't matter. P I, okay, and raised to the power n. Okay. That's because of Feynman parameterization is raised to the power n. And also D, I'll just use D, I'll drop these labels, is alpha j qj square minus mj square. Okay, mj is the mass of the jth line plus epsilon, and j runs from 1 to n, and qj is just a linear sum of k's. So in each line there will be loop momentum flowing and external momentum flowing, so it will be a linear sum of those. Okay, you have to sum them up. Okay. But the coefficients here could be 1 or 0 or minus 1 depending on whether that momentum flows or not. So it will be non-zero if it flows, and whether q is in the same direction as k will determine whether you have plus or minus, and the same thing here, and that we denoted by kj eta jr beta j m, and here r is labeling the loop momentum, so it goes from 1 to the number of loops, and there is something wrong, beta j m pm. M labels the p, so it goes from 1 to the number of external momenta that you have, which I think I was calling capital M. We are here, okay. So that's the integral you are interested in looking at, and you very good. Is it okay? Anything else missing? Okay. Now we want to know when is this integral singular, and we had two conditions. One, the denominator should vanish, okay, so that you have potentially a divergence, a singularity, and second, the contours should get either trapped or should the Yeah, the momentum, the contours relevant to those alphas and k's should either get trapped or should not change the value of d if you were to change them. This is all we had done, and we had written down the conditions for trapping the contours for these variables. So where was that? You remember the condition? It's you sum over, you take a particular loop J and you sum over all the lines in that loop J, okay, and the following should be 0. Eta I j alpha I qi is equal to 0, where you are summing over all the lines I which belong to loop J. Okay, and that should be for each J. So if you have some loop here, there are other things happening. If you are looking at this loop J, you have to sum over all these lines, take the QIs, multiply with the corresponding alpha I, take care of eta ij, and that should add up to 0. Okay, that's the condition we had on the K's. Right, the Q is a linear sum of K and P. The external momenta you have fixed. Okay, the poles move around as you change the values of P. P corresponds to the Z which we have in our first examples, right? Are you following? Are you with me? Okay, so basically it's a constraint that is basically a condition or K. P you have chosen. Okay. So d equal to 0 and these together form what is called Landau equations. Did I mention that last time? No. The denominator being 0 together with these conditions to be satisfied are Landau equations. So what we have seen yesterday is that if a line is off shell, then the corresponding alpha parameter that multiplies that line should be 0. Okay, otherwise your denominator is not going to vanish. Okay, if the line is on shell, then I should satisfy this condition so that the pinching happens. Okay, so I'll just repeat: off shell lines have their corresponding alphas 0. On shell lines, for them I should ensure pinching by this. Okay.
This will give you singularity.
This
they are not.
No, not about.
You cannot deform contour and get a finite answer. That's all.
That's all. Yeah.
You cannot deform because
deform.
These two conditions are, if they are present.
Okay. So almost yes.
Operational definition.
No, almost yes. If this was only the condition, then it's that we don't know whether the surface on which d is equal to 0 is actually similar, because we are not forcing the contours to be pinched. Okay. Here that is what we have tried to do, so that it is really singular. But even this does not guarantee, this condition does not guarantee, or these conditions do not guarantee that really the contours are trapped. Because remember how we arrived here. We said let's take the derivative of the quadratic part corresponding to kj, a loop momentum kj, and say that the two poles corresponding to kj, they collide. Okay. Now when you impose that condition, all you are being able to say is that the poles collide. If this is the contour, if the poles collide this way, then the trapping happens. But if the poles collide that way, trapping doesn't happen because contour is here, right? But my condition doesn't know whether the contours are coming this way, the poles are coming this way to trap the contour, or they are coming this way. So these are necessary conditions. This must be satisfied. But even after these are satisfied, it's still possible that the integral is not singular because trapping is not really happening. Is this fine? So, what I was saying? Correct. That's what I was saying. So you see, not only there is a constraint on, there is a condition on Q, alpha is also having a condition, because you have to solve this system of equations to obtain alphas and Qs, which will satisfy that. And also, if you, so we can ask, like, what kind of solutions you are going to get which satisfy this set of equations. So if I take P's to be real, okay, and let's say I want to take alphas to be real, let's see whether I have a consistent set of equations that satisfies that. So if alpha is real and I take P's to be real, okay, then if you just look at the set of equations here, with alphas real, you will have solutions which are real in Q. These are linear equations. So Q is real, P's are real, which means K will be real. The loop momentum will be real, meaning the pinching is going to happen for real values of K. So it will not be in the K plane, Kj plane, it will be not away from the real axis, it will be on the real axis. The pinching will happen there. Okay, they will be forced to take real values. Okay, so that is all consistent with our requirement that momenta be real. And anyway, so let's proceed. So these are the conditions for, necessary conditions for pinching to happen, and any alpha which does not appear in this one, okay, is irrelevant. Okay, that's anyway, that line is irrelevant because that corresponding alpha is 0. So any line with alpha equal to 0, meaning any line which is off shell has alpha equal to 0, does not enter here because that alpha is not here. Okay, it doesn't change the condition. So that's not relevant for determining the pinch. So what I can do is, you take your Feynman diagram, take the lines which are off shell and just ignore them because they are not relevant for the pinching condition. See, when you draw a diagram, you have all these lines, this and that. You are saying this condition should be satisfied by the momenta, that D should be 0. But in that counting, in this, say D equal to 0 is anyway there, you are on that surface. Now the additional condition that you need to satisfy here does not, in this condition, that alpha which is 0 does not enter, which corresponds to the off shell lines. That doesn't enter in this condition. So that doesn't matter to me. So what I'll do is, I will just remove it or reduce it to a point.
So suppose I have a double box. Then all the internal lines, they are off shell. So it will be a 4-point matrix or what?
Yeah. So let me proceed a bit. I'll give you some examples and then it will be clear what we are doing. But this point you agree, right? If a line, see, what are these? These are constraints on the Q's. But if some Q, because it's off shell, does not change this condition, doesn't add anything to the condition, I don't have to worry about it. Okay, that's all I'm saying. I'm saying a simple thing. So I'll reduce that line to a point. It's not there for me. Okay, such a diagram that you get from there is called a reduced diagram. Okay, and you understand the reason why I'm making a reduced diagram. So, and this will give you a pinch surface. So it's a reduced diagram. Take your Feynman diagram and then reduce the off shell line to a point. That is how you generate reduced diagrams. Okay, which is just basically saying that line does not matter. Is it fine? Nothing special I have said. Okay, good. Now we have all these conditions, and we should solve and find out under what conditions that pinch is going to happen, and does not look like very easy problem to do. Okay, trying to satisfy and figuring out all the loop momenta and all the values of alphas, which will do that. Now I'm going to give you a very nice trick, and it is extremely simple, which solves our problem now, okay, of figuring out how to get solutions of these. So here is the trick, and the trick is this. Okay, so now I have a reduced diagram, and all the lines are now only all in shell lines. Okay, all the lines are on the mass shell. So take a Q in the take a line QI, which is on shell, okay, in your reduced diagram. Now, since this is a on shell particle, real particle, I can write its momentum QI mu. Okay, let me drop the label if you wish. Q mu I can write as, if it has a mass m, then its momentum is mass times velocity, okay, over d tau. Very good. Now I do the following. I'm looking at this particle that's on shell. Okay, it's moving like this with mass m. I say that tau is no. So I want to interpret x mu as a function of tau, giving the real trajectory of a particle. Remember, this is something I am imagining right now, because what you had were Feynman diagrams. They are in momentum space. We are working in momentum space, but here I am creating a classical picture. Whether that picture is going to work, it's good or not, we have to figure out. Okay, but right now I am just imagining that picture, whether I can attach such an interpretation. So, so I really consider it seriously, saying that q mu I will write as this, where x mu tau is a classical trajectory. So the displacement which a particle moving with momentum q mu, okay, the displacement delta x mu is delta tau, the proper time that passes, over m times q mu. Is that okay? That's simple. There's the same equation I've written for finite interval. Okay. Sorry? Yeah, thanks. Okay. Now I'm getting a lot of good ideas, good inspirations, because someone else has done. So I'm just copying it, so I can claim that I'm getting those ideas. I say, let me write delta tau over m as alpha. These are not my ideas. These are ideas by the people who did that long back. Let's write delta tau over m as alpha. Okay, I just give it a name. So that we define that an alpha. So delta x mu is alpha q mu. Okay. Now let's think this, whether it will work or not, but just try. I literally start taking these points, these vertices, seriously, and let's say I want to interpret these 2 points as the displacement between these 2 points as being given by alpha q mu. Right? So you have a physical on-shell particle going from this vertex to that vertex. I'm saying, okay, by um, I'll assign a classical trajectory to it. I will write the displacement between, I will write the displacement that happens as alpha times q mu, where alpha has the interpretation of delta tau over m. Okay, and now I want to see whether I can interpret that displacement as the displacement between these two vertices, whether that is doable. Now, for that picture of mine which I want to impose to be meaningful, and I can imagine anything, that's not a problem, but that has to be a meaningful thing. Okay, for that to be consistent, I should have the following. If I start from this vertex, I go here, some displacement happens, I go there, some displacement happens, I go there, some displacement happens, I go here, I'm back at the same point, meaning the space-time displacement in moving around a loop should be 0. Given any loop, it should be 0. If I'm able to ensure that, then I'm able to ensure that the displacement in space-time between any two vertices is independent of the path you take to reach that vertex, starting from this one. Is that okay? Okay, let me repeat because some of you are not. For this picture where I really assign the displacement by this, okay, this interpretation I give, for that interpretation to work, where I also include the fact that the delta x mu is given by the the distance, or if I take these vertices as space-time points, then the displacement between these two space-time points is given by this. That is the interpretation I want to impose, right? But for that interpretation to work, I should ensure that when I come back to the same point, traversing a loop, okay, the net displacement should be 0. After all, I'm at the same point. Or equivalently, if I start from one vertex, reach another vertex, going from this vertex to that one and that one to this, or I start from here and reach from here to there, the displacements, let's call that is delta x1, that delta x2, these two should be same. Agreed? Now we have to see whether I can push my picture further and have that condition, that requirement satisfied.
This alpha is not same as one of the final parameters.
Well, at this stage not, but in a second it will be. Okay? At that stage you can write beta, no problem. Okay. So before I move further, let me also try to have this picture for massless case, because here m is non-zero, so dividing by m makes sense. But let's also have it for massless particles, if you have massless particles in the loops. So look at this ratio delta t over q0. So you have some momentum q mu, okay, and that particle is moving. Sometime delta t, you are looking at it in some frame. Delta t is non-zero. It has some energy. That ratio is Lorentz invariant, right? Because the way delta t transforms, q naught also transforms the same way under Lorentz transformations. So that's a Lorentz invariant ratio. And that's the same as this. Okay, for now, right now, it's for massive case. So what I'm doing is, I had this here. I've written it in a form which I can then use for massless case also, because the reference to mass is gone. Right? So delta t over q naught okay. So the time in this picture, the time, this is what I call alpha, right here. So that's the alpha. So the time of propagation delta t is alpha q naught. Yeah, just alpha times q naught. Okay. So I can apply the picture that I was developing here for massless case also, and in this case, delta x mu, which is delta t over q0 q mu. Okay, you can see from here delta x mu q mu, and delta tau over m I have written delta t over q0. This is just delta t times beta mu, okay, where beta mu is the forward velocity 1 Is that okay? So I can talk about space-time displacement even in the massless case with this set of equations. So whatever picture I wanted to develop will work for both massive and massless case. Okay, that's what we have in both the cases now. Look at this. What does this equation say? This another equation say if you start interpreting things in this manner. If you identify that alpha with that alpha, okay, then it is saying if you sum over all the lines in the loop J, then that sum is 0, right? These zetas are 1 or minus 1. Okay, 1 when your q is in the same direction. So let's say this is 1 for one line. That's alpha q. That's the interpretation would be. If I identify that alpha and this alpha, then that's the displacement when you go from this vertex to that vertex, because the line joining between them, okay, that's on shell line, and that I interpret as a displacement. You go there, again some displacement, the next one alpha to q2. You come back eventually, the sum is 0. So the net displacement as you go around a loop will be 0, which means that the displacement between any two vertices is also going to be independent of your of the path taken by these lines. Okay, so you go from this vertex to that vertex and so forth. Meaning the assignment of this kind, which I wanted to have, is consistent with this. So I can consistently make that picture, right? You agree? No. Okay, maybe you'll agree after some time, but for now let's proceed. So I have a consistent assignment. I can really interpret these lines in the Feynman diagrams as on-shell particles of mass mi moving in a classical manner from one point to another. Is that okay? That's what the condition is saying, which means your solutions to Landau equations is going to be provided. I mean, you will find those solutions if you could show that a given reduced diagram really corresponds to a classically possible scattering process, right? Because when two lines are meeting at a vertex in the Feynman diagram, that is equivalent to two on-shell lines meeting there, and these lines proceed to something else. They have different momenta, so it's really these to scatter or merge and give out different lines, right? So if such a process is possible, then these conditions are satisfied, because after all the picture that I have produced is consistent with this one. Are you following? Or for that thing to be satisfied, I should have such a picture. This picture is called Coleman-Norton picture, or something of that sort. Yeah, it's called Coleman-Norton picture. Coleman or Coleman. So what's our goal? Our goal is to see if I take a reduced diagram, meaning I've put d equal to 0 constraint, and then whatever I get, whether that is consistent with the classical process. If it is, then you are really on the pinch surface, potentially on the, provided that additional thing I said. Is this fine? Up to here it's okay. So I'll provide you with two examples, and we'll be able to make some analysis to tell when the pinching is going to happen. And with that I will stop. Unfortunately, we have run out of time to talk about infrared divergences. But whatever we cover here should be enough to proceed further, and you can of course look at review and references therein to analyze Feynman diagrams for collinear and soft singularities. And as I said, these are necessary conditions, these are not sufficient, so you have to do something more. Okay, you'll have to analyze which coordinates are intrinsic and which are normal, but anyway, that I leave out. So let's take two examples. Any questions so far? Okay. So let's look at a 2-point correlator. Okay. 2-point function you take. These are one particular irreducible diagrams. I am taking because if you have one more, it doesn't matter. Whatever applies here works there also. So that's why I am looking at one particular irreducible. But if you are not so comfortable with this, think of a 2-point function at some loop order. That is as good. Okay, that is what we can do. Okay, so I want to see under what conditions the Coleman-Norton picture will be satisfied, right? Under what condition this will really correspond to a particle coming and doing something here, and doing something means because you have a lot of lines, right, in the Feynman diagram, meaning create, and then all of those should correspond to on shell lines. So meaning one particle coming in, or source providing some momentum p, and then it splitting into several on shell lines, and then all those on shell lines or all those on shell particles merging together to give back again the momentum p. If that can be satisfied, then I will have a singularity. Okay, you will be on a pinch surface. Is that okay? So that's simple. So we are looking for, we seek a classical process in which a source carrying momentum p, and you will soon see that it has to be off shell. With on shell you will not have the Coleman-Norton picture satisfied or Landau equation satisfied. P can split into a set of on shell particles. Okay, and they later combine into one particle, this one. Okay. So let's say you have this incoming particle of momentum p, you are in the rest frame of it. No, okay. You are you are in the rest frame of it. It splits into two particles. These particles are each of mass m. So let's assume that I am looking at a theory with only one species of particles, only one particle in that theory of mass m. Okay. So now this guy splits and gives you two particles. You are in the rest frame, so they should be going back to back, right? These are identical particles, they go back to back. Is this process allowed? Okay, let's have some, it's fine to be wrong. Huh? Not allowed. Anyone else? Not allowed. Allowed? Not allowed. Because? No, momentum conservation is not a problem. I'm allowing momentum conservation. So you have a particle, it splits into two, they go back to back. You arrange that the momentum is 0. So if that is p, that's minus p. That's fine. That's not a problem. No, one mass meaning all the particles have to have the same mass. You cannot have particles with mass m1 and mass m2. Two different. All the particles in the theory will have the same mass. That is what I meant by one mass. So let's think again. One particle of mass p, you can choose to analyze this in any frame. So let's go to the rest frame of p. It splits into two particles, two on-shell particles. You understand the connection? Because I'm looking at two lines in here, inside this. Okay, let's say at one loop you have two lines. Is this process possible? That this splits and two particles mass of same mass, they go back to back. They won't be initial. Why? Okay, I can arrange that part by taking the required off-shell momentum. So whatever you take, accordingly I will adjust the initial one, so that I have a proper off-shell momentum which allows this. Right? You're right. You cannot have these on-shell, that on-shell will not work. But you take the initial momentum off-shell. Now, is that allowed? Will it work? Works? Classically it will work. Let's have an opinion. With some basis, the basis might be wrong, but okay. So this guy splits into two particles of equal mass and they start going away from each other. But if they start going away from each other, they never meet. This guy goes there, this guy goes there. But your reduced diagram, they have to meet again, right? Remember, these are particles. The way you are interpreting now in that picture, these are particles in really moving in space-time, right? And they meet together at that point. But the one we said just now, they just go like this, right? So they will never meet. Provided, we'll go slow on this, okay? I'm not in a rush. We are anyway not going to reach the infrared place. This part is clear, right? This will not work. But there is one condition under which this will work. And that also connects to what I think it was discussed in several sessions, especially Saurav, I remember, because I attended only that one. Can you think of, remember, we are thinking of the PIs, right? PI is in your hand. That's the only thing you have in your hand. And then you are searching for the conditions to be satisfied by the loop momenta. Okay, let's think. You have again a particle of some off-shell mass. You have already said it has to be off-shell. Okay, it splits into two particles. And my constraint is that they should meet again. So this. It splits into two particles and the conditions are such that they stay there. You are at the momentum that you have, incoming momentum is at the threshold of producing those two particles of mass m. You have no extra energy, right? So they will not move away. They are there. They stay there for a while, some time, that time is determined by the delta t, which is alpha times whatever, and then they combine again. Now that's the classical picture which is possible, and that is what is going to give you the singularity. Is this okay?
How they will combine? There must be some interaction to combine.
They will combine this. That's not the problem. Our issue is not how, whether that picture is consistent. Okay, so they will combine again. I mean, if you were allowing them to split, then they can combine also. Is that okay? Which means I have see what we were searching. We were searching for that configuration of external momenta. In this case, it's only one, which will lead to that singularity, and we have found that one. Not every possible external momenta will give a singularity, because it will not be consistent with the space-time picture that I have. Only when you have barely enough energy to produce the particles on shell and they are not moving. Okay, you are at the threshold. Now you could be at a threshold of producing 2 particles, or you could be at a threshold of producing 10 particles, or whatever number of particles, right? So this splits into 20 of these. They are all sitting here, and they combine. Is that fine? So let's see. So I have equations here, but I don't think I need to write this simple kinematics. You can, whatever I said in words, you can check that this is all fine. So if you are at the threshold of producing 2 particles, so those two go and combine, then P square should be 4m square, right? If you produce n number of particles, then your external momenta should be this. Or if your external momenta is any of these, then you are at the threshold, and then you are going to get the singularity, not otherwise, for the 2-point function. Is that fine? And this is something you already know. These are called normal thresholds. Okay, and these are related to the unitarity cuts, right? Because you have studied, right, cross section. You have studied about unitarity. You cut all the lines, split the entire diagram into 2, okay, and that relates mod m square to the cross section. Anyway, these are your normal thresholds, and that's a picture you can have. So let me give you. Okay. So for this one, you have really 2 lines combining, 2 on-shell lines. Momentum P is equal to, incoming momentum P is equal to 4m square. And if you have, let's say I want to have 4 particles, 4 real particles running in the loop. No, this is 5. So, and then you can have this. Okay, that's also possible. So you could have a reduced diagram like this, and at every stage you should have 4 lines, otherwise your constraints will be not satisfied.
But at the middle point there will be.
That is fine. That's at that point the momentum is see, you are imagining all these particles combining and this. So that's the place where they combine, but the momentum is still conserved. Everything is on shell. Okay. What you should not have is, at any place you should not have 3 lines running or more than 4 lines running, or less than 4. So this is another threshold which happens at p square equal to 16m square. That's at 7 loops. So if you are not in the rest frame, then the same thing looks like all these particles moving collinearly to each other, right? So this particle splits into n number of collinear massive particles which are moving collinearly. They all have mass m, and that produces a singularity. Okay, I'll give you another example. Picture is clear, right? So let's go to another example. Let's take the So here's something I forgot. I'll leave it as an exercise. It's easy. Find out that alpha 1 and alpha 2 are equal and they equals half. And you know the condition on the case or the Q's equivalently. They should be collinear. Right? In a general frame, they will be moving collinearly. Okay. And with equal energies, by the way. They are particles of same mass. Unless they have equal energies, they will not arrive at the same time at the same place to annihilate. So that's the condition on K, and that's the values of alphas. You understand this, right? We are determining what the K's and alphas are, and I'm giving you that answer in the words, but that's the answer. So let's look at another example. So imagine you have been given some Feynman diagram with a lot of complicated number of loops and lines, and you reduce it, meaning you reduce all the option lines to point, and you end up with the following diagram. So some point A, B, C. Let's label the momentum flowing here as Q1, Q2, and Q3. And that is Q3 minus Q1. Q3 minus Q, that's correct. Okay. So this I have obtained by reducing. This is a reduced diagram obtained by reducing all the official lines to a point. Okay. Now I want to know the pinch surface for this. Okay. Meaning whether I can associate whether such a thing, or equivalently for what configurations of momenta will this correspond to a classical picture of particle scattering, right, or merging together. So let's say p square is greater than 0. That's p that enters here, meaning it's time-like, which means I can go to a frame in which this can be taken at rest. Okay, so I go to that frame where it is at rest. Then what's the picture? It would look like you have two particles going away from each other. Right? Similar situation to as the previous case. It's the same thing. Up to this point, it's the same picture. So two particles are moving away from each other. But now they should meet at a later point. So these go, and it comes back and meets at a later point. Can that happen? And under what conditions will that happen? So you are in the rest frame of the momentum p. So you can imagine a particle with momentum p is here. It's time-like, so I'm in the rest frame. And then it splits into two particles of momentum q1 and q2. So to conserve the momentum, they have to go back to back. And they should meet later. That can happen provided you have a wall here with which this guy collides, starts returning, and eventually meets there. Right? So that's a picture which is possible. Now, depending on what is the momentum transferred by the wall, that's the wall. Someone else is providing momentum, injecting momentum to this particle. Depending on that, this guy will meet this particle sooner or later. So you have a classical picture which is valid for this process, which means you are going to get a singularity from such a process. Is that okay? So that's also possible. So what you should do is figure out the values of momenta for which this will happen and the values of alphas. But it's clear that this is going to happen, which means depending on what external momenta you have chosen, these values will change, right? But the picture will hold, that is clear. So these are the methods that you use to find the pinch surfaces, and of course you have to now, for the gauge theory case, you have to include massless particles, and they are very simple, because if you take a Landau equation, the sum eta ij alpha I qi equal to 0, in that if you add any number of soft lines, okay, let's say the parameters are beta alpha k qk, where qk is 0, right? It's a soft line. That doesn't alter the equation because that contributes 0. So you can add any number of soft lines, there's no problem. Similarly, for collinear thing, a massless line can split into many massless lines, that you can add any number of those, okay, and still satisfy your requirements, and you'll be still on the pinch surface. That's what you use and find out pinch surfaces. But then you still have to do more, because you are not just interested in the potential singular surfaces. You are interested in knowing whether it's actually singular. So these were necessary conditions. Now you have to worry about this. What is the opposite of necessary? Sufficient. You have to worry about the sufficient conditions. Okay, so that takes a while, and then you can at the end show that all the divergences in the gauge theories, other than UV, you are going to get from the configurations where the particles are soft or on-shell collinear particles, okay, and they can be factorized from the hard scattering. So that's the story which proceeds, which is after this, and you can hopefully with these techniques you can easily read those literature or books. Okay, I'll stop here. If you have questions, please ask. Okay, no questions.
How does this help in studying Allman diagrams, arbitrary number of loops, and etc.?
So it will not give you the result for diagrams. It will just tell you what configurations give these kind of similarities. So then it will tell you about, okay, these are the soft and collinear ones, which are the ones which are responsible. Then after that you look at the integrals, and what you do is you have, let's say this surface is singular, that's the pinch surface. Then you decompose your coordinates, all these k's, into normal coordinates and intrinsic coordinates, meaning some coordinates which will keep you on the surface. So as you move, you are moving on the surface, and orthogonal to this. And you find out how fast. So as you go in this direction, you are away from the pinch, so no singularity. So you find out the rate at which that happened, so you'll scale with some factors, find out how fast the divergence appears as you approach, and with that you do analysis of, and eventually the end result is you are able to show the factorization of soft and collinear pieces. Yeah. But I think if this much is understood, the remaining parts are not very difficult, at least unless you have a really tough problem, but they are understandable. They are manageable. Tools are these tools.
Coefficient of soft and collinear similarities.
Sorry?
Can you predict the coefficients for soft and collinear similarities in the matter for some process? Let's say we take quark and quark and funnel state is Z. So what type of similarities will come at 2 loop or 3 loop or
are you talking about like branch points, branch cuts, these kind of things, or you're talking about the coefficients of the poles?
coefficient of the poles?
That will be from expressive combination. This analysis cannot tell you what will be the coefficient. This is telling you for what external momentum configurations these things will happen, and what will be happening, what loop configurations will correspond to those singular regions. Okay, then I'll stop.